Welcome to suffering. Anyway, now we'll be looking at cubic functions, how to draw them, everything you need to know about them. So the cubic function formula is pretty standard, right? Here's the formula. Some important things I think we need to discuss about a cubic function is first, how do I know how a cubic function looks? Because a cubic function can start by decreasing, or a cubic function can start by increasing, right? So how do I know which one it is? So firstly, I want to bring your attention to your A. If your A is positive, you start off by decreasing. If your A is negative, you start off by decreasing. So Futlako, does that mean that don't overthink it? All you know, or all you need to know, is if it's A positive, don't even think about the whole shape. Just tell yourself, if A is positive, we need to start by increasing. So you start by increasing. And then of course, it's going to look something like this. You know for a fact it's going to look something like this, but you know it's going to start increasing, then it's going to decrease, then it's going to increase. Maybe. But now you know how it's supposed to start off. So the start is very important. And you know if it is decreasing, if it is negative, right? Your A is negative, it starts off by decreasing. So already here, this graph's A must be negative. Hence, it's decreasing like this. So that's the first thing I want to point out to you. The second thing is whatever your D is, that will be your y-intercept. So D is your y-intercept, because y-intercept is where x is 0 and x is 0. You know, all of this will end up being 0, and then you'll be just left with D. So D is always your y-intercept. Why am I saying this to you? Because there are some times where they will give you the y-intercept, and you need to look at the y-intercept and say, you know what? That's my D. So you already know D. You already know D from this equation. Now, something that I think is very important for us to know is the gradient of a graph is negative where the graph is decreasing. Because the gradient in layman's term, it's saying as x increases, y does this. So if as x increases, y increases, well, that's good. That would mean a positive gradient. So think about it. As x increases, y increases. As x increases, y increases. As x increases, y increases. So we have a positive relationship between them right now. So since we have that positive relationship, our gradient, right, is the relationship between your y and your x. Our gradient is positive. Now come here and we see if x is increasing, what's happening to y? When x increases, so from here to here, y decreases. X is increasing, y is decreasing. X is increasing, y is decreasing. Because of that, what do we know? We know that here, our gradient is negative. So we know a gradient is negative here. We know it's positive here, which means what? When the graph is decreasing, the gradient is negative. When the gradient is negative, the graph is decreasing. When the graph is increasing, our gradient is our gradient is positive. When our gradient is positive, our graph is increasing. Those two imply one another. So they can try to trick you a bit by saying, for example, from this point to this point, the gradient is positive. You know, that means from this point to this point, the gradient is increasing. Don't let them trick you. And then there are 3 points that are very important. Those are number 1, your roots. You always start out by, actually, no, you don't have to. Start out by looking for your x and your y-intercept. So you start with your y. So that 4 points, not even 3. You start with your y, right? That's going to be the first thing you do. Then you fetch your x-intercept, and I'm going to teach you how to do that. And then you fetch your turning points, and then your point of inflection. Your point of inflection is the maximum or minimum, right? Let me repeat it. The maximum or the minimum. One last time. The maximum or the minimum gradient of the graph. So we must think vele here, right? When your point of interflexion, so okay, if you're really thinking about it carefully, there your points of interflexion, what's happening here? Your gradient is positive and positive and positive and positive and positive. So since from here to here your graph is increasing, your gradient is positive from this point to this point. I want you to never forget that, because they like saying, what is the maximum minimum point of your, what is your maximum minimum gradient? So what you're always going to do is you're going to first get your points of interflexion, which you get by getting your point of interflexion is where the second derivative, so you derive once, you derive twice, where that second derivative is equal to 0, and then that x value is the point of interflexion on this thing. So you already know, let's say it's 1. That means this point right here on the graph is your point of inflection. It's the maximum or minimum. And it makes sense, right? This is 0. Your gradient here is 0. Your gradient here is 0. So what's going to happen here? You can see you're increasing. So your gradient is increasing. So it's going from 0 and it's going up, 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 up. Then at your points of inflection, what's going to happen? Your gradient is going to start decreasing until it's all the way to 0. That is for this shape of graph. If we have the other shape of graph, what's the other shape of graph? This shape of graph, what do we know? Your gradient is 0 here. We know here your gradient is positive. Here your gradient is negative. So what's happening? Your gradient from here to here, what's going to happen? Your gradient from, oh yeah, sorry, this is positive, this is negative. So this is 0. So from here to here, we're going to start decreasing. So your gradient will be -1, -2, negative whatever, right? Until we get to the minimum gradient. And then it'll start increasing until it gets to 0. Does increasing mean that it's going to become positive? No. It means it's moving to the positive side. So you could have that your gradient here is -10. And then now it's going -9, -8, -7, -6 until it's at 0. So just because your gradient, right, is decreasing to get to 0 does not mean your gradient becomes positive, right? It's becoming less negative. Let's put it like that. It's becoming less negative. And the same thing is true here. You know here you're increasing. So you're going to reach a max, let's say, of 270. Let's say your gradient is 270 right here. You're going to reach a max of 270, right? But you're going back to 0, which means what? You're going to decrease. You're going to go 220, 2 whatever, 9, 5, 2, whatever, until you reach 0. So between these two turning points where you have a gradient of 0, they're trying to steal all my money. Okay, I've sorted that out. Oh, okay. Okay, sorry guys, I've sorted that out. So while these 2 points, yes, this is 0, yes, this is 0. But you can see here we're increasing. What did we say? When we're increasing, your gradient is positive, which means this, we're going from 0 to 1, 2, 3, 4, whatever, 27, right? And then after that, once we reached our max at our point of interflexion, we start decreasing. The gradient is decreasing, not the graph. The gradient starts decreasing until we reach 0. That is why our gradient is a parabola. But we'll get to that in a few seconds. I'm actually a liar. We won't get to that in a few seconds. I want to teach you firstly how to find the roots of your cubic function. Before I even start with this, I want to say again, like I said before, you do not know how your graph is going to look. You cannot assume how your graph is going to look. If I did not say it before, I'm saying it now. You cannot assume how your graph is going to look. You are not Desmos. You are not whatever, machine learning, whatever, that knows how to generate a graph. You are a person. So you do not know how your graph is going to look. Don't make assumptions. Some graphs don't look like this. Some cubic functions don't look like this. Take, for example, I want to make an example. I'll take a piece of paper. There we go. Take, for example, f at x equals 2 x cubed. If you were to graph this, you would find out that it looks something like this, right? This is a cubic function. Some would say this is the most standard cubic function, but notice one thing: there's no maximum and minimum point. There's no maximum and minimum point. This is the most famous cubic function because it's the most simplest. There's no maximum and minimum points. Number one. Number two, do you see how there are no roots? The only root here is 0. So you can't assume it's gonna have 3 roots. How do you know? How do you know that it's gonna have 3 roots? Don't assume anything about the graph. You can assume stuff using the formula. Like for here, we know our a. Our a is 1, positive 1. So we know it's going to start increasing, right? We know our y, where y is 0. Our y-intercept is going to be where y is 0. No, our y-intercept is going to be where x is 0. Where x is 0, what do we get? This equals to 0. So we get our y-intercept is 0. And now our x-intercept, we're going to get the same thing, right? Here, we don't need a special method. We're just going to say, okay, if the y is 0, then it's going to leave us with x cubed. And then you just cube root this side, you cube root the 0 side. And then you're going to get x equals to 0. So you can get the y, you can get the x. And you know, because of your a, you know, we start by increasing. You know, this right here, this is going to be my what? This is going to be my root. But you also know this is going to be your what? You know that this is going to be your stationary point, right? Your first derivative. It's going to be 3x squared, where this is 0. 3x squared. You're just going to end up with x equals to 0. So here, you're going to have a flat thing because the gradient here is 0. Do you see? You get so much for your graph. But if you came into the test where now you're like, I know how it's going to look like this, and then nothing's working out, and you're freaking out, and then now, you failed. So don't assume. Just take a breath, gather as much information as you can, then do what you need to do. This is a simple example, but usually to find the root is not that simple. We use a method, I use a method called synthetic division. If you use a different method, then synthetic long division, it's fine, I don't mind. I call it pseudo long division because, yeah. Oops. Okay. So, firstly, what do we know? We know that we need to look for what we call a divisor. A divisor is a number in which when you enter it into your function, this is an example of a function, right? We're going to be using this function today. You enter it into the function is actually supposed to give you the y value is 0. So what you're going to do is you're just going to get in your calculator and you're going to start from 0, and you're going to go both to the positive side and the negative side of the number line. You're going to say 0, 1, negative 1, 2, negative 2, 3, negative 3. You're going to substitute all those values in until you get one where x equals to, f at x, which means the y value. So when you substitute that number in here, it gives you 0. So luckily for us, I did that and we started, luckily for me actually, when x was 1, we got 0. So I have my divisor is 1. You see, I did the whole thing. I showed that my divisor is 1. Now that we know our divisor is 1, we can start our method. The first thing you're going to do, right, like long division, you're going to give this guy a nice little balcony here. You're going to put your divisor. Then you have your coefficients. Where did you get these coefficients, Putako? Use the coefficients of all the terms in f at x. Use the coefficient of all the terms in your cubic function. You see, in our cubic function, we have 4. So we have 4. We have 1. So I put 1. You have negative 26, negative 26, 21, 21. Don't bring the x. We just want the coefficients. Arrange them in order of highest, or let me not even say highest. Arrange them in order of descending exponents of x. So this has the highest, this has the second highest, this has the third highest. You know what happens if, let's say you didn't have x to the power of 2. What you would do is say, right, you'd force x to the power of 2, but you'd say plus 0 x to the power of 2. So you'd first fix this, so you have it like 3, 2, 1, right? And then you'd want it to be like that for every polynomial. This doesn't just stop at cubic functions. You could have anything, and it would, this long division, pseudo long division method would work. So you have your coefficients that you got from this formula. The next thing you're going to do, you're going to bring the 4 down, like similar to long division, right? Bring the highest, the coefficient which has an x with the highest degree, you're going to bring it down. And then you're going to multiply your divisor, right? You're going to multiply it by that coefficient. So we bring the 4 down, then we say 1 times 4. 1 times 4 is positive 4. So you see here, I say positive 4. The product of these two, you're supposed to add it to the next coefficient. So positive 4, 1 plus positive 4 is 5. If we do that over, let me just erase quickly. Okay, I come back. I hope this is actually recording. Like, I'd be so embarrassed if it wasn't. Do I think it's recording? I do think it's recording. Okay, let me not get in my head. We have 5. The 5, we can just say 1 times 5. It gives us positive 5. See how I'm putting it in a bracket? Because I don't want drama. Bracket, right? What does that give us? It gives us positive 5. Hey, focus. Positive 5, right? Plus negative 26, which is going to give you negative 21. Then you say the divisor again. We do the same thing we did. The divisor times the thing we brought down, the integer we've brought down, which is negative 21. 1 times negative 21 is negative 21. We add negative 21. Bracket again. Don't start things. It gives you 0. So the main thing we want here is at the end, once you've done this cycle over and over again, you must get 0. If you do not get 0, you did something wrong. Another thing I want to stress is you want to make sure that you have the lowest divisor. If you take a divisor that is higher than this one, right, you will, I'll show you later, but you'll end up factorizing correctly, but that factorization that you've just did will not lead you to your x-intercept. So you can't just pick random numbers. You need to make sure you start 0, 1, negative 1, 2, negative 2, 3, negative 3. That's the only way you can get the lowest. I know it's annoying in a test. You see your time is running out and you're busy here, 0, 1, negative 1. But really, guys, just pay attention, be diligent, so you can get the marks for what you're doing. Don't focus on the marks you haven't gotten yet. Focus on the marks you're trying to get right in that moment. So yeah. Next thing we're gonna do. Okay, so I just wrote this on the next page, whatever. Now we're factorizing. So you're gonna say, but like, where did you get this? You know your divisor is 1. So when you put in the bracket, you're supposed to say x minus 1. Hi everyone, sorry, my phone switched off. So what I was saying is, you know your divisor is 1. You're going to say, but like, why did you say x minus 1, right? The 1 you get from your divisor. Do you know when you have your formula for a parabola, right? There are 2 ways your formula can be, but one of the ways your formula can be is when you have a binomial, which is like x plus or minus p, right? Plus q, and then this is squared, right? This can be one way where the form that you find your parabola. Your parabola is a curve. Your parabola, you're going to see there are a lot of relations between the two. But basically, you know that if, let's say, your p is 1 here, let's say it's x plus 1 squared. What does that mean? That means outside of your bracket. Well, I'll say it again. That means outside of your bracket, when you get the x coordinate, right? You know that this is not positive p, it's negative p, which means it's negative 1, 0. This is for parabola. So here we're following the same logic. You have found one of your x-intercepts. That's what you did by finding the divisor. You found one of your x-intercepts. Your x-intercepts, one of them is 1 for this function. So now when you put it in the version of the formula, you're gonna say x minus 1, opposite sign, just the way you do when you do your parabola, just the way you do when you do your when you do your hyperbola. So do you see here that the curves lie and they trick you? Don't be tricked by the lying curves. Anyway, what you're always gonna have in the next bracket is your trinomial. What we're doing right now is we're writing f at x in a different manner, right? Ignore these zeros for now, right? So you're always gonna have a trinomial. But like, how do I get my trinomial? You know your trinomial is a coefficient x squared plus a coefficient x minus a coefficient. It's not a coefficient, it's an integer. Since there's nothing, it's coefficient too. But it's an integer. So what you're gonna do, you're gonna take these numbers down here, right? You're gonna say 4x squared, 5x, negative 21. They make up your trinomial. So you take the integers from down here below this line that we've made. Once you're done with synthetic division and you put them in, then you simply factorize this trinomial. You factorize it and there you go. And from here, you can find the x-intercepts. For example, because now what we're going to do is, let me say f at x, right? F at x. So now you have the formula for f at x, right? You're looking for what? The x-intercepts. The x-intercepts are where y is equal to 0. Hence, I wrote the zeros here. Do you see? Hence, I wrote the zeros here. You can just leave it as f at x, and then once you get it like this, then you can make it 0. Okay, anyway, hence I put the zeros here, right? This is normal factorization. You know this when you do it all the time. You get your critical values, you do whatever. You don't need to do that in this case, but you're factorizing normally. So you have x equals to 1, or, right? 4x equals to 7, x equals to 7 over 4, or x equals to negative 3. And there you go. You have your 3 x-intercepts of your gradient. Bada bing, bada boom. The last part of the video. Yeah, this is the way you shout in triumph, like, yes, I'm free. You guys are indeed free. So, right now we have a curve. I want to talk to you about the relationship between a cubic function, this cubic function, its first derivative function, there's the first derivative function, and the second derivative function, I want to talk you through the relationship between all of them. So when you see a test, you know logically. Now, this is an important part. This is the logic part. Logically, how am I going to go about this? This tells me about that tells me about this. You want to be a master of calculus when you answer your test. So masters of calculus, what do we know? This is a cubic function in which the a is positive. How do we know that? Because it starts by increasing. If it starts by increasing, the a is positive. Perfection, right? So this is a cubic function I've given you. We have our important points. We have our y-intercept, which isn't important in the relationship of everything. It's not very special, the y-intercept in this relationship. But we have our x-intercepts, right? We have our turning points, and we have our point of interflection. B is the point of interflection, like you see. A and C are turning points. Butlako, what does this imply? Let me ask you a question. The graph, now just answer to yourself, you can pause the video. The graph is increasing, which means the gradient is what? The gradient is positive. From here to here, the graph is decreasing, which means the gradient is what? Wait, let me think. Yes, you're at 0, then you're going to have your minimum. But like, how do we know we have a minimum here? Because the graph is decreasing. So you have your minimum point, which means what? The gradient is negative. We can all agree? We can all agree. So from here to here, the gradient is negative. And from here to here, the gradient is negative. Because why? It's very simple. Don't overcomplicate it. When the graph is decreasing, the gradient is negative. When the graph is increasing, the gradient is positive. Is the graph increasing? Yes, the gradient is positive. Is the graph decreasing? Yes, the gradient is negative. From here to here, the graph is increasing, which means what? Our gradient is positive. This is going to come useful. What else do we know? We know that the point of interflexion is our maximum or minimum gradient. Our maximum or minimum gradient. Okay, so it's our maximum or minimum gradient. Here we can tell these gradients right here are positive. These gradients are positive. These gradients are negative, which means what? It can't be our maximum, because this from here to here, all the gradients are negative. And here, they're positive. So you'll never find a negative number that's bigger than a single positive number. It's not possible. So this point of interflexion has to be where we get our minimum gradient. So you see, when they go, oh, what is the minimum gradient? Now you know. Let me get my point of interflexion. Let me see how this graph is looking. Let me map out its behavior. So that's important, because now we're going to get into the first derivative graph. Guys, they won't always give you a cubic function graph. They might give you this graph, the first derivative. They tell you this is the graph of the first derivative, and from here you might even be expected to draw out your function, if that makes any sense. So don't be fooled. Don't let anyone fool you, right? You're not anyone slimmer, right? We're all good, right? So don't let them fool you. Let's attack. We said this is a graph of the gradient. So x is the x values, y is the gradient values. Y is the value of the gradients. So let's go back to what we said. We know at the turning points, you are going to have what? You're going to have a graph, right, where your gradient is 0. The gradient is 0. So notice with our parabola, we're going to have these 2 points. At A, you're going to have a gradient of 0. At C, you're going to have a gradient of 0. Don't even worry about the parabola. Just worry about this. 0, 0. That makes sense. We're all on the same page. This is your minimum point, where your gradient is at its minimum. So at the point of interflexion, in this case, with a graph looking like this, is the minimum point on this graph. Okay, but like, what's the minimum point of this graph? What does that even mean? It being the minimum point of this graph means that we know for a fact we have this point, and we know that our parabola can never be smaller than this. So already we know that it should look like this. But let's think about it more. We said before A, our gradient is positive. Look here. Our gradient is the y. Everything is above 0. Everything is positive. We can see that from A to B, right, B being the point of interflexion, our gradient is negative. Look here, from A to B, your gradient is negative. We know from B to C, our gradient is still negative because the graph is still decreasing. Look here, still negative. Oh, I see what's going on now. And then we get to this point where it's 0. What's happening from here, right, upwards? What's happening? For every x value after C, we can see that the cubic function is increasing infinitely so, which means it's increasing, which means our gradient is positive, which means this y value must be positive. Do you see how we've come up with this? And of course, if this was formulated differently, like if it looked like this, right, this parabola would be the opposite. Your POI would be your maximum point, because it'd be from down here to up here. From here to here, we are increasing. Oh, let me focus. From here to here, the graph is increasing, which means everything is positive. From here to here, everything is negative. So here, we can only have the biggest, the maximum gradient at our point of inflection, or at B, I guess one could say. Focus. So our parabola would look the opposite because the graph would look the opposite. So just by seeing this, you also have another idea of how your graph is going to look. Do you see how, yes, they can make a question challenging, but they won't necessarily like trip you up that much. So don't let them play with you in the test. Just calm down and think. Now we have another point, and the other point is our point of inflection, right? Not our point of inflection, our second derivative. So we've done the cubic function, the first derivative of the cubic function. Let's look at the second derivative of the cubic function. What do we know? We know that at the second derivative of the cubic function, right, this b is now the turning point of this parabola, which is the first derivative graph. The turning point, what is the gradient at this turning point, right? Because this is now we're doing what? Deriving this, right? We're deriving this. So what is the turning point? What is the gradient here? It's 0. So our linear function has to intersect here at b. And that's all you really get to know. You don't get to know any more. You can just know where it's intersecting. And of course, you can see that from here to here, we're decreasing, right? So that means the gradient is negative of this graph. The gradient of this graph, the gradient of the gradient graph, if you will, from before b is negative, which means that here we'll have what? Remember, the y is the value of the gradient. It means here to here, we're going to have a gradient that is negative. Oh my word, I drew this wrong. We all make mistakes, guys. I apologize. From here to here, it's decreasing. So actually, your gradient is going to look something like this. Negative, right? And then it's going to hit whatever point it was hitting. Then it's going to be positive. Because we're decreasing, right? We're decreasing. Then we hit 0. Then we're increasing. So it's supposed to look the other way around. We all make mistakes. You've seen the mistake I've made. So yeah, the only critical point you have is here is B. Now, to test who's watched the videos, don't write a whole paragraph. Tell me, how does the the third derivative of this function look? That means the derivative of this, right? How is that function going to look? Not what is that function, but how's that function going to look? And derive it from this formula right here. You see, I've derived them while I was going along. This is 6ax to b, sorry. Derive it for the third time. And then tell me how it's going to look out as a graph. And I'll know that you've watched all the videos. And I'll heart your message. And I might, I don't know. I'll think about taking it easy on you guys. But probably not. Anyway, guys, that's all we're doing for today. Tomorrow, we might do optimization. I'm sending your test forward. Your test will not have optimization. Do the test. Your test is due at midnight. So midnight, you must have submitted your test. Good luck.